In this video, we're going to look at velocity time graphs. Now, in the previous video, we looked at displacement time graphs or distance time graphs. Velocity time graphs are a little bit different. So in a displacement time graph or distance time graph, the gradient gave the velocity, but in a velocity time graph, the acceleration is given by the gradient. And also a horizontal line, like in this one. In the last one, that meant your displacement wasn't changing. But in this one, it means your velocity isn't changing, so it means that it's a constant velocity. And also, very important one, the distance travelled in a time interval is given by the area under the VT graph, and we can use a lot of different things here. So let's look at these three graphs. This one, sloping upwards, means it's got a positive acceleration, no acceleration in horizontal line, so constant velocity, and then it's slowing down, negative acceleration. Okay, right. This example says, finding the area under a VT graph often involves finding the area of a trapezium. Learn this formula. This is the worst learned formula out. People do not like to learn the formula for a trapezium. So let me just look at this formula here very quickly. If you've got a trapezium like this, for example, and it was 6, we'll say 10, and we'll say 4, they're all centimeters, so 4 is the perpendicular height. The area of this is given by a half a plus b times h. Now a and b are the parallel sides and h is the perpendicular distance between them. So the parallel sides are 6 and 10, the perpendicular distance between them is 4, and that can be tidied up. That's a half times 16 times 4, and do that whatever way you want. I would do half times 4 is 2, times 16 is 32, and that's going to be 32 centimeters squared for the area of that particular trapezium. Okay, so you need to know and understand that, and also quite often the trapeziums you find are going to be like vertical trapeziums like this. This is still a trapezium, so maybe that's 2, maybe that's 4, maybe that's 6. You could work out the area of that trapezium in this one, not go through it, but it's going to be a half. My parallel sides are 4 and 6, perpendicular distance between them is 2. You would just work that out. So you need to be familiar with your area of the trapezium. It saves you a ton of time. It saves you a ton of time because sometimes people will break it up in triangles and rectangles, and also the odd time it is the only way that you can do it. So be careful on these. So don't just think you can get away with it without needing them. Sometimes the only way you could do it is with the area of the trapezium formula. Okay, it says here in this one, a car is moving along a straight line as shown in the VT graph, velocity time graph. Describe the journey and find the distance travelled by the car, and then what is the displacement of the car from its starting position. Okay, right. Now, you need to write this, and I'm not going to write this in because my handwriting's so bad, but what would be happening here is this first bit, the car is accelerating from rest until it reaches a speed of 24, and then you'd say it maintains this speed for a further 6 seconds, so that's this bit, and then it decelerates to rest in a further, I think that's 8 seconds, a further 8 seconds. So you'd write in those things. I'll just write it in now. Apologies for my terrible handwriting. So the car accelerates from rest, and they like putting in words like rest, to a speed of 24 meters per second, and it does that in 4 seconds. We'll say maintains a speed for 6 seconds, so it goes from 4 seconds up to 10, and then what it does, it decelerates. I'll just mean slows down, and decelerates to rest again, and then in 8 seconds. Okay, decelerates to rest in 8 seconds. Okay, right. I'm going to get rid of that just so I have some space to do this. I could maybe get it squeezed in, could I? Right. It says, what is the displacement of the car from its starting position? Okay, so from its starting position, so Right, it hasn't actually gone back on itself. This is a distance away from where it started. It's continued at the same speed. It's slowing down, but it's still moving in the same direction. So all of these are still going away. So don't get confused with your displacement time graphs. Your distance is equal to your area. So we just need to work out the area. Area is equal to a half a plus b times h. We're using our smart way of doing it, the trapezium formula. So it's a half. My parallel sides, this first parallel side is from, top one here is from 4 to 10. So that's 6. The bottom parallel side is 18. You can see that. And the perpendicular distance between them from 0 up to 24. So 24. Fire that into your calculator. Let's just tidy up a wee bit. That's going to be 24 times 24. And then divide by 2 or times by half times 24 times 24. Even just do that. And we'll do the job. And that will give you 288 meters. Lovely. Okay. Next question says, next example says, a particle is traveling in a straight line. It has a velocity of 10 meters per second when it is subjected to an acceleration of minus 2 meters per second squared for 8 seconds. Draw a velocity time graph for this interval of 8 seconds and find the change of displacement and the overall distance covered in the interval of 8 seconds. Okay, right. Let's just draw a wee diagram again. You've got your velocity. That's in meters per second. And then there's your time in seconds. Okay, now this wee thing is going along merrily at 10 meters per second. And then it is subject to an acceleration of minus 2 meters per second squared for 8 seconds. Right, I think this would be a great opportunity to talk about our units of acceleration. So meters, well, the way they've written it here, which I don't like, is ms to the minus 2. There's nothing wrong with it, but I prefer to think of it as meters per second squared, or you can think of it as meters per second. So if you think about it this way, that's what acceleration is. It's a rate at which your velocity changes each second. So if you are accelerating at 2 meters per second squared, that means your velocity is going up 2 meters per second each second. That's really what it means, each second. So if you are decelerating, so your acceleration is minus 2 meters per second squared, that means your speed is going down by 2 meters per second each second. Okay, so if you were going at a speed, of 10 meters per second, and then for 8 seconds you're decreasing your speed at 2 meters per second each second, so that's from this, that means your speed has gone down by 16 meters per second in those 8 seconds. So in 8 seconds, I've gone down to here, and that is going to be then minus 6. So from 10 down 16 takes you to minus 6. And also, you'll go from 10 to 0 in 5 seconds. So that's what we've got. Okay, so there's your velocity time graph drawn. Find the change in displacement. Okay, let's work this out. Then we're going to have area 1, and I'll call that area 2. So let's just work all of this out. So my area 1, first of all, it's just the area of a triangle. So it's a half times the base, which is 5, times the height, which is 10. If you did that out, you'd get 25 meters. My area 2 is going to be a half times 3 times 6, which is just going to be 9 meters. So we've got, these are both two distances. So part 1, the change in displacement is going to be 25 minus 9, which is going to be 16 meters. But your distance traveled then, your overall distance is going to be 25 plus 9, which is going to be 34 meters. So you can see here the difference. That you had 25 was in the, sorry, that 25 here was in the positive, but this was in the other direction, so they counteracted each other a wee bit for displacement. But for distance, total distance is out this way. Here I had gone 25, and this way we'd worked out I'd gone a distance of 9, and this distance, 25 plus 9, is 34. Okay, right. Couple more to go here still. Oh, a nasty wee one next one. Okay, right. It says here, a ball bearing is dropped from a height onto a horizontal metal plate. Each time the ball bearing strikes the metal plate, it rebounds with its direction of motion reversed and its speed reduced. Sketch the velocity time graph of the ball bearing until it strikes a plate for the first time. Okay, right. Now, velocity, this is a lot more complicated. Zoom in on this. So here, you've got your initial velocity of 0. If you drop something, its initial velocity is 0. As you drop it, it's going to speed up. Okay? And what's going to happen is, this here, I'm just marking this on, this is the first hit. That's when it hits the ground first. So it speeds up until it hits the ground. Once it hits the ground, it instantly, I should say, changes direction. And we're going to go half as much. And it changes direction. So then it starts again. And it's instantly got this half of the speed, we'll say. It rebounds and it rebounds when the direction of motion reversed and its speed is reduced. So notice what I'm doing here. This distance from here up to here is greater than this distance from here to here because the speed's reduced. Okay, so that's tricky. And notice as well, these lines I'm drawing are parallel to the one before. So at this point, this is my speed is 0. This would be at the maximum height. Okay, and then this is going to be my second hit, so it hits the ground another time. Do your vertical line. Remember, it's changing direction, so don't go down all the way down as far. And then it goes to here. And then again, this is going to be its new max height. And then it hits again. This is the third hit. So it hits until it strikes a plate the third time. I think that's us. That's the third hit. And just for completeness, I'll just finish that wee bit off. So that is very difficult. Okay, so let me just run through that again. So start off, we drop the ball, so its initial velocity is 0, and it speeds up until it hits. So this is it hitting the ground, and then it changes direction. So that's why we go down to here. So the velocity is now going the other way because it's changed direction, but it's not as great. So this distance and this distance are different because it's reduced its speed. It's lost a bit of energy somehow, so it's reduced its speed. Then it takes off again, and it starts out fast, and then it slows down. It's at a maximum height, and it speeds up as it comes the way down, hits the plate, or hits the ground again, changes direction, but it's less, takes off again, and it strikes again. That is very difficult. Okay, hopefully an easier one this next one. We've got, it's a catching up question using VT graphs. So it says a car traveling at a constant speed of 30 meters per second passes a stationary motorbike. 6 seconds later, the motorbike starts off in the same direction and accelerates uniformly at 4 meters per second squared until it reaches a speed of 40 meters per second. It then maintains this speed until it reaches the car. They meet at time t. Sketch a velocity time graph for the motion of the car and motorbike and find the time taken for the motorbike to reach the car. Okay, right, we have a lot to do here. Let's just get started here with our VT graph anyway, and then we'll worry about the rest. Okay. Right, so first of all, a car traveling at a constant speed of 30. So I'm just going to do a wee mark up here. This is going to be I'll just do my 30 here. And it's a car. It's going along at a constant speed, so I'll just mark on, that's my car. It passes a stationary motorbike. 6 seconds later, the motorbike starts off. So there's 6 seconds. The motorbike decides to get into action, and it starts off, and it accelerates uniformly at 4 meters per second until it reaches a speed of 40 meters per second squared. Okay, so you've got 40, and you're going at 4 meters per second. You're accelerating 4 meters per second squared. That's going to take you 10 seconds then. So by 16 seconds, it's going to be up to the speed it needs to be. It's going to get up to 40, so we'll do our 40 up here just. So there's 40, it starts. I'll mark that on there, bear with me a wee second. I'm doing this without a ruler. So that's going to be 40 up here. And then it maintains that speed until they catch up with each other. So I'm going to say they catch up at this time. Okay, now that's my diagram. It says, so I've done that, and part B says find the time taken for the motorbike to reach the car. Now for the motorbike to reach the car, that means the distance travelled by the motorbike, which will be this area under this curve, onto this diagram as I should say, straight lines, is going to be equal to the area under this rectangle. Okay, so that's what we're going to have. So we're just going to say let them meet when small t equals big T, and then we're just going to set this up. Okay, so for the car's easy. For the car, the distance s, it's going at a constant speed, so s is equal to your speed, which is 30 times your time. And for the motorbike, not so easy. For the motorbike, okay, let's work out a few wee things in our diagram. First of all, this wee length here, this horizontal, is t minus 16. And this horizontal here would be t minus 6. So we're good to go. So, and we've got the vertical height of it as well, is going to be 40. So the distance for the motorbike, s is equal to, and this is just from your half a plus b times h, that's where I'm getting this from. So it's a half times t minus 6 was one of my parallel sides, the other one is t minus 16, and the perpendicular distance between them is 40. Okay, it looks like an absolute mess. Tidy it up and it makes it so much easier. That's going to be a half times 2t minus 22, then times 40. And if you file that in, a half times 40 times 2t is going to give you, I don't know what I've done here, sorry. What have I said there? Half times, that's just going to give you 40, isn't it? Yep, that's going to give you 40t. And then that's just going to give you minus 11 times 40. So that's going to give you minus 44, sorry, 440. There we are, got there in the end. Right, so you've got your two things. What we're going to do now, so we've found those from the diagram. You can see, I'll just let you have a look at that. Once you've got that done, all you want to do then is put the two distances equal. You could just put s equal to s, but that means here we have 30t is equal to 40t minus 440. A wee bit of rearranging, bring the 440 to the left, bring that 30t across, you'll have 40t minus 30t, you'll just have 10t. So 440 equals 10t. A wee bit of working out, t works out to be 44 seconds. Okay, so tricky enough for example. Okay, right, the next one, two ways of doing this. I don't know if I'll do both, I might just do one. It says here, a car travelling along a straight road passes point A when t is equal to 0, so that means at the start it passes point A and maintains a constant speed until t is equal to 24. The driver then applies the brakes. Let me just correct that. Right, the brakes spell brakes the correct way. He applies the brakes and the car decelerates uniformly to rest at point B. Before the brakes were applied, the car had travelled 4/5 of the total distance. And sketch VT graph for the journey and calculate the time taken for the car to travel from A to B. Okay, no idea. Let's get started. Draw a diagram. This is not an easy question. There's a lot to read and reread in these. I certainly don't read it once and have to know exactly what I'm doing. I have to read it a couple of times. Okay, so your diagram, velocity on the vertical, time on the horizontal. Okay, first of all, car is traveling along a straight road. Point A, when t is equal to 0, maintains a constant velocity. So a constant velocity, we don't know what that is. So we're just going to call it v, our velocity v, and it maintains it for 24 seconds. So that's going to be 24. The driver then applies the brakes and the car decelerates uniformly to rest at a point B. So here, it decelerates uniformly to rest, and that is my point B. So that's my point A up here at the start, and there's my point B. Now, it says, before the brakes were applied, the car had travelled 4/5 of the total distance AB, and yep, and that is it. So we're going to say that, call this big T, that's my total time. Call this area 1 and this area 2, and we're just going to look at a couple of ways of doing this. So it tells you that, well, we could work out then that your area 1 is just 24 times V. All right. Your area 2, that was just by the base times the height. The area 2, it's a triangle. It's going to be half times the base. So this wee base here is going to be t minus 24. So half times the base, t minus 24, times the height, which is v. Okay, that's what we've got. So, what could we do? Right, now we know that area 1, this bit here is really, this is 4/5, and this bit here is 1/5. So that means area 1 is actually 4 times area 2. That's quite tricky. So they're told to tell you in the question, before he applies the brakes, he has travelled 4/5 of the entire journey. So that means area 1 to area 2, it's in a ratio of 4 to 1. So that's 4/5 and that's only 1/5, or it's 4 parts of the journey and that the second bit is only 1 part. But whatever way you want to look at it, area 1 is 4 times bigger than area 2. Now this allows us to set up a wee equation. So instead of area 1, write 24V, and then instead of area 2, write your half times t minus 24 times v. Okay, right, I can get rid of all that. Now what we can do here, first thing I'm going to do, I'm going to get rid of the v's. So that's 24 is this equal to a half, 4 times, sorry, a half times t minus 24. And then we'll start tidying up. It's just a nice easy linear equation then. So that's 24 is equal to 2t minus 48. Bring that 48 across. 24 plus 48 is equal to 2t. And 20 plus 40 is 60. 4 plus 8 is 12. 60 plus 12 is 72, is equal to 2t. So your t is 72 divided by 2. T works out to be 36 seconds. And that's it. Okay, that is one method. I quite like that method. I'm really not too sure if I'll show you another method. You know what, I will just leave it at that. There is another method some people prefer, but I prefer this one. I'm going to leave it there with that one. There we go. Okay, so that's our velocity time graphs done, and I think that's our topic done on kinematics. So we've done all of our constant acceleration formulas, vectors formulas, and then velocity time graphs, catching up questions as well. That's a tricky bit of it, catching up questions and so on. Now the next topic I'll go on to is forces, and all of this stuff that we've just done in kinematics quite often comes into force question. So it's as well like a latter parts of the questions. Once you've found the forces involved, you maybe are able to find acceleration, and then it becomes a constant acceleration question. Okay, that's us done.